So this is part 2 of lesson 8 in unit 3, and the general rule we've just been talking about is that this y equals log x base b and y equals log x base b to the n is related by a vertical stretch about the x-axis by a factor of 1 over n. So let's look at these two equations then. So in other words, it just means that log x base b to the n is equal to 1 over n log x base b, because they're related by a vertical stretch about the x-axis. And so this 1 over n is the vertical stretch factor. How does this mathematically, algebraically, these equations relate? Well, if you look at this equation here, log x base bn, we can write that as this equation up here. We can write it as log x divided by log of b to the n, because we have the base b to the n here. Well, this can also be written, we can bring the n to the front, so we can write it as log x over n times log b, and so that will just separate the 1 over n here, so this is really 1 over n times log x over log b, and log x over log b can be written as log x of base b, and we still have the 1 over n, the vertical stretch multiplier here at the front. So this is how these two equations are related. So whatever the base here and the base here, if they are a multiple of each other, then they can be related to each other by a vertical stretch. So in class example 2 here, we have the question, describe the transformation which would map the graph of log x base 3 to the graph of log x base 81. Now we can look at 81 as being equal to 3 to the 4. So if this is 81 is 3 to the 4, it means that 1 over n, this factor here, is 1 over 4 because of this 4 here. So it's a vertical stretch about the x-axis, and of course vertical stretches are always about the x-axis, so it's kind of redundant to keep saying about the x-axis. But it's by a factor of 1 over 4. Excuse me. In the second one here, we have log x base 16 and log x base 4. So how is 4 related to 16? Well, 4 is 16 to the exponent and a half, the square root of 16 in other words. So 1 over n here is really 1 over a half. Well, 1 over a half is really 2. So we have a vertical stretch by a factor of 2. You may want to pause the video here and just go over that and think about that again. And now I'll page down. Alright, so in example 3 here, if log x base 5 is 6, state the value of log x base 125. Well, we can see the 125 is actually 5 to the power of 3. So we can say that this 25 is really 5 to the 3. So we can write that then as 1/3 log x base 5. Well, we know that log x base 5 is actually 6, so it's really 1 times 6. Sorry, a third rather, times 6, which is 2. Then part B says, prove the result in A by converting to exponential form. So let's change this to exponential form and just do drop, swing. So drop and swing and bump the 6 up. X is 5 to the 6. And we can also look at log x base 125 and put that as equal to a value. So we'll call it equal to v. Again, doing drop, swing, bump, we'll drop the x down. The 25 swings over and bumps the v up. So we can change 125 to 5 to the 3 to the v. So that's 5 to the 3v So x also equals 5 to the 3v, so it equals this, and x also equals this. So here we have the statement here, and obviously v, therefore we compare v must be 2. So the value of this is 2. And we basically proved this result up here and here are the same thing. Okay, let's page down. So in example 4 here, we're being asked to use the knowledge learned from transformations to compare the graph of log x base c to the graph of y equals a log b x minus h base c plus k. This is more or less the equation we used in the unit on transformations. But we're taking the log of all of this, b times whatever's in the bracket, to the base c, and they're using c to distinguish it, that it's different from this b factor here. B factor is associated in the unit on transformations, it's associated with a horizontal stretch. Okay, so let's look at the graph of y equals x to the base 3. So graphing that, that's shown here, y equals log x base 3, and it's saying here in part A1, write the transformation associated with each of the following and sketch the graph on the grid. So if we have y equals 2 log x base 3, compared to this here, it's basically multiplied by 2. Or we can say that y has gone to a half y. Vertical stretch by factor of 2. So we can take our y values on the graph of log x base 3 and just double. So it's 0, double of 0 is 0, double of 1 is 2. I'm taking some easy points here, but this is 1.5, so we'll go up to 3, and so on. This one, we've basically taken log x and shifted it to the right by 2. Horizontal translation, right by 2. So where would that go? You can take a point here. It's got an x value of 3, so that would, an x value of 3 here. Yeah, so this would be shifted over by 3. By 2. What am I saying? Okay, by 2. So 1, 2. So that goes to here. This point will land over here. And for example, if we're here, then this will land here, and so on. If we're here, it'll land up over here. Last one here, log x base 3 minus 2. We know that's basically y has been replaced with y plus 2, or it's a translation down by 2. So we can take this point here and put it down here. Take this point here, put it down here. And various points like this one can go down here, and so on. Part B and C here. Do any of the above transformations result in a change in the original domain or range? Well, in this one we are doing a vertical stretch, so it does not change the domain or range. What about number 2 here? For number 2, we know that we're shifting 2 units to the right, so the domain will change. Instead of starting at 0 and greater, x is going to be greater than 2. The range doesn't change. And for number 3, this is a vertical translation 2 units down. Doesn't really change the range, and therefore doesn't change the domain either for that matter. Part C, state the equation of the asymptote. So nothing's changed here. The asymptote is still x equals 0. Same for part 3, x equals 0. But part 2, because we've changed the domain, we've shifted it to the right by 2, the asymptote is now not x equals 0, but x equals 2. Alright, the last part here is investigating the graphs of y equals log x to the n and y equals n log x. In other words, the n has just been brought over to the front of the equation. One of the laws of logs states that log x to the n is equal to n log x. However, are the graphs of these two things identical? Well, they should be. Let's hope. We'll see if they are or not. Investigate by considering odd and even values for n. So let's have a look at that. Here are some of the odd values we can have for n, 3, 5, 7. Here are some of the evens, 2, 4, 6. Let's consider these two equations, therefore, log x of 3 and 3 log x. They look pretty much the same. Same here. If it's 5, then we can bring the 5 over. And the 7 over. What are we really doing here? We're multiplying by 3, by 5, and by 7. And what if we use even numbers? So, if we graph log x to the 2, or log x to the 4, or log x to the 7, it seems we get 2 halves to our graph. Whereas if we just have 2 times log x, we only have the 1 half. Now remember, that must be due to the fact that we have, we're logging x squared. And so remember, when we have an exponent, a variable to an even exponent, this variable could be odd, or could be negative or positive rather. If it's negative, when we square it, it becomes positive. In other words, if it's negative 3, it becomes positive 9, or if it's positive 3, it still becomes positive 9. And because of that, we get two parts, or mirror images, to our graph. If you do a table of values, you'll see that this is the case, or just do it on your calculator. So the graphs are not identical. Interesting. So, just summarizing at the bottom of the page here. If n is odd, the graphs of y equals log x to the n and y equals n log x are identical. But if it's even, then the graphs are not identical. Since the domain of y equals log x to the n, where x is not 0, and the domain of y, where x is greater, let me just read that again because I'm not quite sure what I'm saying here. Hold on. Okay, so what this is saying here at the bottom is the domain of this is just x cannot be 0. X can be positive or negative numbers, but not 0. However, the domain of this, x has to be greater than 0. In other words, we can't log a negative number. We can't log a negative number here either, and when n is even, then x to the n will be positive. Even if x is negative, x to an even exponent will be positive, so we can log it. So when n is an odd number, as in examples up here, we do not get the mirror image, because that's where we have this situation where n is an odd number. We do not get the other side of the graph. In other words, for the domain for this part, x has to be greater than 0. There's no ways about it. We do have the option here that x can be less than 0 as long as n is even. Okay, so please do the questions for this assignment, and we'll see you in class.